Okay, so yeah, today's speakers is Ergun Yalcin from Bilkent University. So it's great to have him. So he's going to tell us about higher limits over the fusion orbit category. So please, whenever you feel ready. Okay.
Thanks. I hope I can make this reasonable non-technical talk, but I have some results that I want to mention at the end, so I have to give quite a few definitions. This is a little bit a kind of topic that has some history and a lot of questions actually comes from similar questions for finite group situation. So I won't be able to tell every bit of the history, but I will try to come to the results as early as possible. So it's about higher limits, some Chromology for category. The category is the fusion orbit category. So I will define both of these. So this is about sharpness problem for subgroup decomposition of p-local finite groups. So now I'll start with definition of a p-local finite group. So this is a generalization of finite groups. Their classifying space can be p-localized, and you want to replace that with something for abstract fusion systems. So this is where p-local finite groups comes in. So what's a fusion system? A saturated fusion system over some finite p group S is a category whose objects are subgroups of S. So objects are p groups inside S, subgroups of S, and the morphisms are some injective group morphisms. They have to satisfy a bunch of axioms. It takes a long time to explain all the axioms, so I will skip that. But the main example of such things, which everything is modeled after, is this finite group situation, that there is a finite group, say, G, and then S is one of the zero P subgroups of G. And what we can do, get this here, we can look at the category FSG, so that whose objects are subgroups of S, and the morphisms are given by conjugation maps by some G element in group G, where the conjugation map means this product X goes to G, X, G inverse. And you can show that such a thing is an actual saturated fusion system. It's satisfying all the axioms, and again, the axioms are just models so that this example is actually one of the main examples. In some ways, you want to, in an abstract way, to repeat what you get from zero theorems. That's the, we can say what the fusion system is. But it's a generalization of this fusion system of a finite group. So a subgroup in S is F-centric if its centralizer in S is inside itself. It contains a centralizer in S. For every Q, where Q is isomorphic to P in F. So up to F conjugation, all the other P subgroups, which are isomorphic to P, have to have this property, that being centric in S property. This full subcategory formed by these objects is denoted by F up C, and this is usually called centric fusion system or fusion system on F-centric elements. Now, the orbit category of a fusion system is a quotient category where objects are same as previous, as the same as the fusion system, but morphisms are modeled out with the inner automorphisms in F, or like conjugations coming from Q will be modeled out. And some people denote this as rep, F PQ, but I won't use that notation. So we have the orbit category, which is a quotient category of fusion system. You can restrict that to F-centric subgroups if you like, and you get OCF, which is the centric orbit category. We'll be dealing with the problem which is high limits over this category. So this is our category where we will be trying to calculate cohomology of. Okay. Now, what's a p-local finite group? That's a triple where first thing is S, a finite p group. F is the fusion system. And there is this third thing, L, that's the linking system. Centric, we'll only talk about centric ones today. Centric linking system associated to F. Again, the centric linking system is also a little bit difficult to fully define, explain. I can just give you some simple things about it. First is objects are F-centric subgroups. It is an extension of FC, the fusion system on centric elements. It's an extension with the, for every P, the centralizer, central P is the quotient, the kernel of this extension. So we didn't have the ZP inside morphisms here in the F-centric fusion system, because we model out, like we look at on the conjugations, if you think away. So we're extending it with possible center elements inside P. And this linking system also should satisfy another condition. Basically, you should have an inclusion map from transporter category of coming from the zero subgroup. Or you could say that there is this distinguished monomorphism, so P inside the automorphisms in L, so that it satisfies certain conditions. Basically, the linking system is where we put some meat into the fusion system by adding the conjugations by elements in P. We are adding the P inside the category, basically, as part of its automorphism group. Again, this is something maybe as abstract category, not very clear, but the linking system is an extension category, so it may not exist. Like, there was a big question about the existence of it, and it was solved by Andy Charmak that such a category always exists. Again, going back to the finite group case, there is a version, there's a linking system you can associate the finite group. Again, you take a zero P subgroup S, F is its fusion system, then subgroup is F-centric. This, for the finite group case, the F-centric condition is relatively easy to understand. It becomes that actually CP should be zero P subgroup of CGP, and that is equivalent to this track sum, isomorphism to this track sum, where this part is the P prime group inside the centralizer of P. We call such subgroups P-centric. Those are P-centric subgroups inside G. So F-centric is equivalent to being P-centric in G. You only look at the category whose objects are these subgroups, P-centric elements, subgroups in S. The morphisms, again, we model out something. NG is all the G's which transports, conjugates P into Q. NGP, usually this thing is considered as the morphisms of transporter category. So you model out that with P prime part of the centralizer of P. You model out unnecessary P prime things, but you leave the CP in it. Again, this will leave the ZP, so it's a larger category than fusion system. And you can prove directly that this category is this fits into that axiomatic system that defines the linking system. So it is a linking system associated to fusion system FSG, and this triple is a p-local finite group. So again, I guess the most understandable example of p-local finite group is the finite group itself, considered as a triple. So of course, these cases are special. There's other p-local finite groups which are not coming from finite groups. But in this case, we call that this p-local finite groups realized by G, if that is the case. So we will be looking at the general case, not just the finite group case, but any p-local finite group. And what is the question or what problem we're looking at is called sharpness problem. This p-local finite groups has its own homotopy theory. So the classifying space of such a thing is the Bose-Feld-Kahn p-completion of the realization of L as a category. And it's a p-local finite group. So this is only a p-localized, p-completed space. And there's also what we call a subgroup homology decomposition for the realization of L. This doesn't have to be p-localized. This is true. There is a homotopy colimit over the category I defined before, orbit category fusion system, where the functors, these exact functors, are the ones that takes every p to its classifying space. I can stop here. If you have questions, we can look at this more.
I have one question.
Sure.
S is a finite group, right? Being a p group.
F is fusion system, so it could come from
S is. S,
F.
I mean.
This
S, S, I mean.
S, yes. S is a finite p group, though.
So why do we say that p-local finite group? Is it possible that to get an infinite group here, a structure here?
This is SSP group, but
okay.
This F and L is induced from an arbitrary, say, a finite group. Like it may not really be p group structure. It is the model for the p like finite group conjugations on a p group S. Right?
So it can be infinite dimension. Okay.
So, I have it may be too philosophical, this question, but am I right in saying that L is determined by F and S?
Yes, but that's a big theorem.
Yes, nevertheless, the term p-local finite group was formulated before that uniqueness theorem was proved. And in the light of the theorem, it now doesn't it seem a bit odd to
use L
to have this concept of a p-local, because the actual given data is just the fusion system.
Yes, I guess you could just say this is the it's all determined by the fusion system. Yes. So you could use BF here if you want, but this is the classifying space of the fusion system. And some people use that notation BF.
Yeah, some people use it. It's become habitual. Yeah. Yeah, sure.
You could use that classifying space of the fusion system. You're right.
Right.
Yeah. Now this subgroup decomposition, there is a similar one for finite groups. That, this is was quite a big work to define and work through this abstract linking system setting. This is done by a paper by Broto, Reve, Oruver, and they proved quite a bit about these linking systems. In particular, they show that the cohomology, I will show that in a minute, but the cohomology of linking system is determined by the cohomology of the p subgroups up to the fusion. So there's a stable element theorem in this setting, which is a quite important result. But this homology decomposition that with the homotopy colimit gives a spectral sequence. This is a Kahn spectral sequence. So let me show that. So this spectral sequence has S and T coordinates. On the S direction, you have higher limits. This is coming from colimit, homotopy colimit. These are the higher limits, S higher limit. And this is the T cohomology of the whatever the object you're putting in. So there is a spectral sequence, Kahn spectral sequence, Bosworth Kahn spectral sequence is converging to the cohomology of the linking system. And this spectral sequence potentially have all these non-zero entries in every S and T. The definition of sharpness, which is the claim will be that we say decomposition is sharp if even in the E2 page, these E2 STs are always 0 when S is strictly positive, strictly bigger than 0, and for all T. So basically, it only have a vertical line as non-zero entries. Every other thing is 0. It is sharpness. So definition of sharp is that, which you can also state in differently. I will state in differently in a minute about this higher limit vanishing. So there are two theorems about this. One is due to Diaz and Park. And they prove that when the p-local finite SFL is realized by a finite group, then this subgroup decomposition is actually sharp for this p-local finite group. And the finite group proof is relatively easy, but it still requires some work. And they have done all that work nicely. And they proved it for the finite groups. The subgroup decomposition is sharp. Another thing is that if you have sharpness, if the subgroup decomposition is sharp, as I said, you will have only one vertical line. That vertical line will have lim 0 of the cohomology of subgroups P inside OSF. This limit of these cohomology groups is equal to the stable elements inside the cohomology of P, cohomology of 0P subgroup. And it is defined as the cohomology of the fusion system. So what Broto-Revo shows is that this L, its cohomology, is same as this limit, and they prove this independently from sharpness, like without having the sharpness. That cohomology of L is actually cohomology of the limit of the P subgroups. This is known as Cartan-Eilenberg theorem. And this happens for finite groups as well, that cohomology of a finite group is equal to the limit of this cohomology of its P subgroups over the orbit category of the group. And this limit, they are also sometimes denoted by cohomology of fusion system. We know there that cohomology of the group and cohomology of the stable elements are isomorphic. And that's called the Cartan-Eilenberg theorem for finite groups. So what Broto-Revo managed to prove is that the Cartan-Eilenberg theorem holds for linking systems. And their proof is quite involved. It uses T-functor theory. Actually, Jihan will remember maybe this paper. They use T-functor theory, and they use quite a bit theory to get this proof. Anyway, because this was a consequence of sharpness, and it's obtained without the sharpness, and this is the sharpness for finite groups, these two suggest that we should really have a sharpness, that this should be true that for all n bigger than 0 and I bigger than 1, ith higher limits over this category of the group cohomology should be 0. And this is what the conjecture is. Today's talk is about. This is called sharpness conjecture. I think Diaz-Park make the conjecture inside in this theorem, in this paper, the theorem is, but there's also other places this is stated as a problem. One place that this is stated is a big long survey by Ashbar and Oruver, where they state a lot of problems and at the end of their survey, and this is one of the problems there, as one of the problems to solve in this area. Any questions on this? This is the sharpness problem. So we will try to prove higher limits of group cohomology functor over the OCF is 0 when I is bigger than 1. So how we prove this, or how we work on such problem? First of all, as a person who works on group actions, I found that lack of group is a big problem. So we don't have a group, we have abstract category. If you don't have a group, you can have a group action, you can have GCW complex, topological space, all of these are missing for me. So I try to make this into a problem about some group. For discrete groups, actually, it's a possibility to make this a problem about infinite discrete groups. So for a discrete group G, you can take a collection of subgroups C, and by a collection we mean something closed under conjugation always. The set of subgroups closed under conjugation. When you have a group and a collection, you can define 4 different categories. The first one is called the transporter category. And this one is the category where objects are, again, the elements in C, but the morphisms are group elements which transpose H into K. So those are the ones that conjugation of H left is inside K. And this is called transporter category over the C. The orbit category, which you must have heard it at least once in these seminars. In the past, we had a lot of work on orbit categories, is the one that, again, objects are C, but the morphisms are given by G maps, G over H to G over K. And you can make an association between these G maps and group elements up to left K multiplication. Every G map is actually this form, and this form things can be associated to left, right cosets of K with G. So in other words, we can actually treat orbit category as a quotient category of transporter category, where we mod out K action from left. So this is how I will think about orbit category of G, as mod out from G, from K. Any question? The other 2 categories, one is fusion category. Fusion is like coming from fusion system also, that the morphisms, again, objects are C, morphisms are conjugation maps, not elements, but conjugation maps with some G. Since they're maps, we don't get anything if it's in the centralizers H. So that means we are actually modding out centralizer of H from this transport set of transports from H to K. You mod out from right with the centralizer. And this is another quotient category of the transporter category. Now, fusion orbit category is where we mod out both. So we mod out the K from left, centralizer from right. That's a category where you don't see the centralizers, or you don't get to see the conjugations by K. In fusion orbit category, we draw a line here above FC. It's close to fusion category. And because you mod out both directions, it is the quotient category of both fusion category and orbit category. So I drew a diagram here to summarize. Transport here, you quotient to the fusion, you quotient to the orbit. If you quotient in both ways, you get the fusion orbit. And that's where we are at. This is what we are going to do. So if you have a group, you usually work with orbit category of the group. You define the chain complexes, Breadon cohomology, everything is defined here in the orbit category. If you have a fusion system for a group, you're working here. But if you remember, if you took the orbit category of a fusion system, it turns out that you get here. So that's why this category will be important to us. So let me say this one in a more official way. So if you have a discrete group, right? So first we have to define what a zero subgroup for a discrete group. A zero subgroup of an infinite discrete group is a finite P subgroup. We only look at finite ones. Finite P subgroup, where every other finite P subgroup is a subconjugate to it. And with a discrete group, you could have a zero P subgroup or not. So it's not like finite groups that you always have a zero P subgroup. You may have it or not. But when you have it, you can define a fusion system. Like FSG will be the category where conjugations are the morphisms. So we say that the fusion system realized by a discrete group if discrete group has a zero subgroup and FSG is isomorphic to F. Now, the good news, or what makes all this possible, is that there is a theorem which says every fusion system, not even saturation is necessary, every fusion system is realized by a possibly infinite discrete group G constructed as fundamental group of graph of groups, finite vertex and edge groups and so on. So there is always a discrete group. Most of the time it's infinite, of course, when it's, which has a zero P subgroup S, where this fusion system is same as the given fusion system. So if you have a P-local finite group and abstract fusion system, you could actually think this is a fusion system realized by some infinite group. And then what does it tell us? It tells us that if you define the P-centric in a nice way, so the nice way will be the ZP is the zero P subgroup of CGP. For an infinite group, you can still talk about zero P subgroups. So you can define this way. You no longer have this product with CP tensor to P prime part because these are infinite groups. This is also an infinite group. But you can define the P-centric. And then if you take all the P-centric subgroups inside G as your collection, fusion orbit category over this collection will be isomorphic as a category to, actually not isomorphic, sorry, equivalent as a category to OCF. And this is the category we are interested in. We wanted to prove sharpness over higher limits over this category. We are now saying that there is a discrete group realizing F. And in that category, if you mod out both directions, centralizers and K actions, the fusion system, fusion orbit category you get is equivalent to the original category that you are interested in. I stated the sharpness problem again. So this is your category. That's the fusion orbit category of a discrete group over collection of P-centric subgroups. We want to find its higher limits, which means we want to find this Chromology as a category with coefficients in Hn, the Chromology of groups. And we want to show these Chromology groups are finite, or zeros, vanishing result. So we got our group. We wanted a discrete group or some group. When you have a group, this is the nice thing, that you have a group, then you have a group. You can talk about these subgroup posets. You could talk about these elementary abelian subgroups. You could talk about other spaces that group can act. Those things are all in your arsenal now. I don't know, I guess Matthew will know this, but you don't have a good notion of L space. Like you can't talk about spaces for linking systems, as far as I know. So this sort of helps us with that aspect, that you can now talk about spaces, for G spaces for this group, and maybe use those spaces to calculate these higher limits. Okay. Now, so what we do, we define something called fusion Braudon cohomology. This part of the talk might be a little bit technical if you are not familiar with topology, but I will have 3-4 slides, and at the end of those slides, I will have a result that we will carry that over. So for a discrete group and a collection, we can define something called the chain complex of ROC modules for, say, R commutative ring with unity. These are chain complexes of not group ring, but modules over the orbit category. This orbit category, remember, is the category where objects are subgroups in C, morphisms for G sets. So G sets were morphisms. How do you define this chain complex? Each subgroup goes to the H fixed point chain complex of the H fixed points of the space, and each morphism is mapped into corresponding morphisms coming from the fixed points. Actually, the fixed point sets are maps from G over H to X, G maps like that. So if you have a map like this between two orbits, then that induces a map between them. This is a contravariant factor. So it's when we say ROC module, we actually mean a contravariant factor from OCG to R modules. And when the collection is large enough, these things will have the form RG over H question mark. So those stabilizers, if they are inside the C, they're actually projective modules. They are projective OCG modules. So this gives you chain complex of projective ROC modules. And I defined this before in these seminars, topology seminars. 5 years ago, we had intense seminars on this. These chain complexes are very useful. To construct group actions, we use them over any group. We can work out this kind of chain complexes. Realizing them gives you space, group actions and spaces. So these are very useful. But this is orbit category, not fusion orbit category, right? Here we have G maps between G over H to G over K, where fusion orbit category, we had a quotient of that. So how do we pass to the fusion orbit category? This is done actually by Luc. I found a paper years ago, actually, written by Wolfgang Luc, where he takes these chain complexes, but instead of H fixed points, he takes H fixed point mod out the centralizers. He used this because his centralizer in his what he was trying to do with term characters, these centralizers were very big, and when you mod out, you get much smaller chain complexes. So he used this idea to calculate term characters. He was working over complex coefficients, so it's not really similar theory, but still the idea came from his papers. So instead of sending it to the chain complex of H fixed points, we are now sending it to the chain complex of the orbit space of H fixed point with the centralizer. So this is what the difference is. Because we mod out the centralizers, now these are actually modules over the fusion orbit category, not the orbit category, but this quotient category. And actually, this is the orbit category of the fusion system, right? So if you think about it, this is where we are getting to spaces. And then the maps here gives you a map between these two. And you can actually extend it to the maps between H to K. So we have found our chain complexes. When you have chain complexes over orbit category, one defines Breadth homology. So if you have chain complexes of fusion orbit category, we should define fusion Breadth homology. And we have this FSCG in subcharacter to denote this. So the cohomology of a space, Breadth homology, fusion Breadth homology of a space, is basically the cohomology of total space of a. This is a Cartan-Eilenberg resolution of the chain complex. So you get a projective resolution of the chain complex. You too apply Hom, and then you take this cohomology. This is a double complex, so the cohomology is the total complex of a double complex. looks technical, abstract, but this is very useful. The reason is that this is a double complex, right? So double complexes gives you spectral sequences. So we'll get a spectral sequence out of this. And that's how we calculate the cohomology of the fusion system. So what the spectral sequence you get out of this is you actually get two of them. They actually work for fusion orbit category or orbit category. Whenever you have a GC double complex X, you have this chain complex. To make it in one statement, I use both categories. I don't distinguish that. And I use this notation to either for this or modding out with the centralizer. So what happens is that when you have a GC double complex, and if you have an M OCG module, then you have a chain complex which converges to the Breadon cohomology of the space. These two spectral sequences are corresponding to filtering the double complex, either in the vertical lines or horizontal lines. And this one uses these coefficients. I write these coefficients here in an explicit form. These are the ones actually cohomology of the orbit space of H. So at each H, you are calculating cohomology of either the orbit category or fusion orbit category for the H. So you have to restrict everything to H, and then calculate the cohomology of the orbit category. And those are the coefficients. This is very useful. You can see that if you have a good space X, you can actually decompose your cohomology that you want to calculate, Breadon cohomology, as like a spectral sequence where you are only needing the calculation of cohomology of isotropy subgroups of the space. So if you have a good space where isotropy subgroups are smaller, then you only need to know something in the smaller subgroups, the cohomology of the fusion orbit category of smaller subgroups. Of course, it's a spectral sequence, so it will have differentials and difficult calculations may arise and so on. And this is the Breadon cohomology, so it may not be equal to the cohomology of the fusion category that you're trying to calculate. So there are two problems. One, this could be like Breadon cohomology may not be the cohomology you want to calculate. It's not the cohomology of the category. Second is that you may have differentials on the spectral sequence. But still, it's a kind of idea which is used in induction theorems, like finding spaces where you can find this isotropy, gives you cohomology of the smaller things you want. And this is a very general idea to do these things. So how we overcome these two problems? First, we can replace the Breadon cohomology with the cohomology of the orbit category if the homologies of the space is just homology of a point. So because of this spectral sequence, which requires homologies, if you have an X which is acyclic in some sense, has only homology at the 0 dimension, then this will be the same as the homology of the orbit category. So that's one observation. That gives us our main theorem, which I will, for this, this is the main technical thing we're using. So something is called as GCW is called acyclic, ROC acyclic or RFC acyclic, if the chain complex at every H fixed point is homology of a point, or the orbit space is a homology of a point. So these are acyclicity conditions. And then if you have an acyclic CW complex, any ROCG module, then again, this denotes the cohomology of the OCH. Then you have a spectral sequence converged to the cohomology of the OCG, the orbit category. So no longer there's a Breadon cohomology, fusion Breadon. You just have the cohomology of the category. And we only need to know the cohomology of the OSC for subgroups which are isotropy subgroups of X. So if X has no fixed points, for example, you just can use this as some sort of induction theorem for the OCG. I can pause here. I don't have to. It's technical, but essential idea is that you had some abstract category, linking system, fusion system. In that category, you had a homology decomposition, which required computation of some higher limits, vanishing of those higher limits. Because it's abstract category, we found the infinite group, which realizes that fusion system, and which the category we are interested became the fusion orbit category of this infinite group. Now, this infinite group has group actions on spaces. So we're saying that if you can find a good space, which has either this property or this property, then you can calculate cohomology of that orbit category using cohomology of its orbit category of its isotrope subgroups. So you can find a inductive argument for vanishing theorems if you can find a space, a suitable space. That's what we are saying. I'm sure you have seen similar ideas before. This is how people do subgroup decomposition theorems, sharpness of subgroup decomposition. Finite groups also use the same idea, but stated in a different way. This is what we're going to do. So the space, what spaces you should have? Subgroup complexes are good. So we have two actually spaces that works. One is we call this Dwyer G space, which is E of AE. So this is the homotopy colimit over the Coulomb category of G or E's. So that's this is the Dwyer space for centralizer decomposition. And it is over the collection of elementary and P subgroups, non-trivial elementary and subgroups. This space, surprisingly, have not only the first one, but the second one also holds. So that H fixed points of this space is known to be contractible for P subgroups, non-trivial P subgroups, but it's not obvious that fixed points mod out with the centralizer is also contractible or mod P acyclic, and that requires about 2-page proof, but you can actually prove that not only the P subgroups, but after you mod out, you still have an acyclic complex. Other one is the subgroup. This is the poset of subgroups. Ramos knows this, I guess, right? The poset of P subgroups inside a group G. Ramos has a theorem on this for the finite group case, I believe. That poset has a contractible orbit space, right? So here we take the subgroup poset and we say that for every non-trivial P fixed points is contractible, but also the quotient with the centralizer is still mod P acyclic. The difficult parts, again, the quotient with the centralizers. This one is easier because the contraction is, we can show that's equivariant contraction, so we can make this work. But the spaces that we use turns out to be spaces that comes from subgroup complexes or Dwyer spaces, otherwise, for these complexes. And we directly plug these into this previous theorem. And this thing have stabilizers of this space are the centralizers of elementary abelian groups. The stabilizers of this space is the normalizer of P subgroups. So we will have reduction to the centralizers of elementary abelian subgroups or the normalizers of P subgroups. or normalizers of chains of P subgroups, to be correct. That's induction, like that's how our induction will work. This will give you stabilizers are all centralizers of elementary groups, and these are the normalizers of chains of P subgroups. And they're both acyclic, so we can apply the theorem before. Now, if you look at this theorem here again, I have this spectral sequence where Higgs points of this space. So this could be in this category or this category. So that's why the acyclicity is important. Right? Get this, but also the stabilizers are important because that's where you get this Chromology calculate on the stabilizers. Okay. Now, again, this is the centralizer, this is normalizer. So we get results out of these two. One is centralizer spectral sequence for the Chromology of the orbit category. This is the theorem. Again, a little technical, but what we are trying to get this Chromology of OCF, any coefficients m, we're saying that you have a decomposition through this spectral sequence over the elementary abelian subgroup, limit over this category of elementary abelian subgroups, where calculations of centralizers, centralizer fusion system of E, Chromology of OCF has to come here. And this is there's a similar spectral sequence for groups, finite groups, and that's called centralizer decomposition of a classifying space. But here we have the OCF version of it. And direct consequence of this is that if these are all trivial, vanishing result, if these are all trivial, you can play with it a little bit and prove that this becomes trivial. So the main theorem actually in a while before this talk is that the subgroup decomposition is sharp for every P local finite group with non-trivial center implies that the sharp group decomposition sharp for every P local finite groups. Again, this is only possible if you can reduce the question to the non-trivial center pieces, and those are the ones which are the centralizers of elementary subgroups. This is our first theorem, I would say. Do you have a question? I have a few minutes. There's one more theorem I want to state, but if you have I mean, this is a technical looking thing, but just focus on this, what it says. This is the Chromology of what you want to calculate, OCF. And this says that there is a limit process, higher limits spectral sequence where the pieces are Chromology of the whole of CF, so centralizers of elementary groups. So if these are all trivial, which we can assume, this is the assumption in this theorem that they are going to be trivial if they have a non-trivial center. These all will be trivial, so everything will collapse to a horizontal line. And then this is where you get, you have to use something else to say that. It gives you the vanishing of this. And the other important theorem, remember we had two spaces. The second one was the one that subgroup complex. That gives you another spectral sequence, but you have to subdivide that complex into, so the objects becomes the chains of subgroups, and you stabilizers of chains are normalizers of chains in the fusion system. So for that case, we have a similar spectral sequence. Again, we have higher limits of over the subdivision category of this fusion system. Again, the objects are chains and morphisms are sub-inclusions of chains so NF is the stabilizer. So we have the OCNF as the Chromology calculating here, and you can actually calculate cohomology OSC. The only catch is this theorem only works with p-local coefficients because it uses some theorems that only holds for p-local coefficients. And this is the induction theorem to the normalizers. We have a similar result here. If you all the normalizer, these NF deltas are NF sigmas have vanishing cohomology, then you want to say that this is vanishing. Here, though, it says strangely, you can prove that these are all zero because this will have, these are the normalizers. So this will be realized by a finite group. These things are actually realizable by finite groups. So these all vanish. But then you get a horizontal line, and we don't know that cohomology on the horizontal line vanished this time. And the cohomology on the horizontal line is familiar cohomology. It's the cohomology of this thing, cohomology over the complex of coefficients in the normalizers, cohomology of the normalizer. And this is a local coefficient cohomology. So we only get that the cohomology we want to calculate is isomorphic to the cohomology of these stabilizers, of this GC double complex, basically. This is actually local coefficient cohomology. But we don't get we don't know if this is trivial. This is actually the somehow what controls the sharpness of the normalizer decomposition, which is introduced by Liebman, Asaf Liebman. For any p-local finite group, there is a normalizer decomposition, and the normalizer decomposition sharpness is equivalent to these things to be zero. So we get some sort of propagation result that sharpness of the subgroup decomposition is actually equivalent to the sharpness of the normalizer decomposition. And I asked Asaf Liebman if he knows anything about the normalizer sharpness of the normalizer decomposition, and he said he doesn't know if it's true or not. So this links to two possible sharpness for the p-local finite groups that you could ask. To be honest, there is also a centralizer decomposition and sharpness question of that, but I didn't mention that it actually goes into here, and it is known that centralizer decomposition is sharp for p-local finite groups. So this is what we use here, but we don't know the same result for normalizer decomposition. That's why we couldn't finish in some ways the sharpness of the subgroup decomposition. If we knew that normalizer decomposition is sharp, we will conclude the subgroup decomposition is sharp, but we couldn't because of this not known for normalizer decomposition. Okay, this is all. Thank you. I'm sorry it was a little technical. Thank you.
Okay, thank you very much. Any questions for Ergun?
Yes, I have some questions. Well, I have a short question and a long question. Maybe I'll ask my short question and then have someone else to turn. This sharpness for when there's an OP of F is non-trivial. You were working with centric subgroups there.
Yeah.
So can you do that with quasicentric subgroups?
I don't see why not. I guess the paper that I'm using, Broto, Ravi Oliver, it uses only centric ones because it's the first paper on this field, on this area. So many of the results I have to check. Like I don't know if this is true for quasi or things like that.
The advantage of quasicentric subgroups is that they're closed under extension by central subgroups. or under reduction to subgroups of S that are central in the fusion system. So I wonder if it might have some advantage for inductive arguments.
Oh, yeah, it probably will. I mean, the question will be if you can show OCF is all QF is isomorphic or not, right? So you have two categories including each other, and maybe their higher limits are equal.
Right.
Those kind of passing from one category to other one, sometimes you can prove that, but they require, like in finite group theory, in finite group case, the usual orbit category higher limits are actually equal for collections of all non-trivial P subgroups and all centric subgroups. So anything in between, you get actually same higher limit. So in that case, if you take the collection of quasicentrics, you will get the same higher limit. But that's for finite groups. So for fusion systems, that passages, I couldn't prove any passage like that. I tried to prove it from non-trivial P subgroups to the centric ones, and I couldn't prove it. So, and I asked actually Diaz about it, and he said he doesn't know any theorems passing from one collection to other one. That will be the challenge.
Right.
But, it's a good direction. I mean, it's definitely interesting direction too.
Well, my other question is sort of, because I'm resistant to spectral sequences, of course. Well, things vanishing on E2 pages can often be reformulated in some other way. I mean, does the vanishing of that, does the sharpness conjecture, can it be expressed in some simpler way? Say exactness of some sequences or something like that.
In some ways, yes. I mean, this is a Chromology of a category, right? We already stated independent from the spectral sequence, right? We're saying that if you calculate Chromology of this category, right, with coefficients this, you get 0, right? But how you calculate Chromology of category? You take your projective resolution, you apply home, and then you calculate cohomology of that cochain complex. So the vanishing will mean that that cohomology is 0, which means that you get the exact sequence.
Yes.
So the
so can you formulate that exact sequence?
That means that if you take the constant R and resolve it as a projective resolution over this category and apply home to it with these coefficients, you get the exact sequence. Now, this cohomology is important because if you apply any home with any M here, it's not going to work. This is being cohomology of groups is actually important. Actually, there is a similar conjecture which says that if you replace this to any functor which comes from a Mackey functor, so you can extend the concept of Mackey functors and finite groups to Mackey functors over fusion systems. Diaz and Park actually tried that direction too. So you can make this a Mackey functor over fusion systems are defined, and you can restrict that to any collection. So they ask that this is 0 if this is coming from a Mackey functor. That's the more general version of this conjecture. So that will mean that if you resolve this, apply Mackey functor to it, you get the exact sequence. And that's kind of thing that they will depend the resolution of this. And I mean, there's a canonical resolution, of course, for every category, but that will not be very useful for this case. You need to maybe find some clever ways to make it a question about just Mackey functors. Don't know. I don't know. But I calculate some things with small cases like S3, and it easily gets very, very difficult to connect this to the Mackey-Functor theory. But there's a expectation that if you replace group cohomology here with any Mackey-Functor, anything that comes from a Mackey-Functor defined on all subgroups of S, then this should still be zero. That's the expectation.
But cohomological Mackey-Functor.
Yes, yeah, cohomological Mackey-Functor. Cohomological Mackey-Functor. It's interesting, actually. The Diaz Park has a paper on Mackey-Functors for fusion systems, and it's quite interesting to see how that develops.
Okay, any other questions?
Maybe I have a question. So the construction of X depends on G, right? And the construction of G depends on the graph selected, I guess.
Yeah.
So changing the graph, could that be helpful in induction? I mean, maybe choosing some other graph.
So the infinite groups that we use depends on the construction. If you remember, Ahmed worked on this graph of groups and realizing fusion systems. We were with him. We wrote a paper calculating cohomology of the group, and that comes from this. And if it gives the cohomology of the fusion system in some cases, and so on. So there we looked at all possibilities of different groups. These groups, of course, changes the vertex groups, I guess. Are the normalizers. There are two ways to get these groups. One is by Revistenko. Those are HNN extensions with. For those ones, you have all the vertex groups are P subgroups. And edge groups are actually even also P subgroups. So, but still they're kind of hard to work through. And then for the for the Robinson construction, the vertex groups are normalizers of certain essential P subgroups. You can take them as P subgroups of centric subgroups. But they're infinite groups. The construction gives you infinite group, and the normalizer of those are infinite groups inside the big group, although the vertex groups are finite. One place this shows up when you try to prove certain results about fusion systems. They show up which groups you're using, but other than that, I don't know if they show up in the, I mean, I didn't use or I didn't make in connection to the spaces actually construct. So there could be by changing this, you automatically changing the wire spaces, subgroup or set. So it could be some way to get more accurate information, but yeah, I don't know.
Okay.
I don't know the full answer to that.
Okay. Thank you.
In hand calculations that you can do things, but for general things, I don't know if you can do something. I was tempted because this is just a graph of groups. It has a two-step resolution, right, with the stabilizers of these groups. And I was tempted to apply the quotienting out with the centralizers in that short sequence. This is sort of what we were looking at with Mohammed too. When you quotient out that two-step permutation complex, you actually get a non-trivial homology. So those doesn't become exact. So this has a graph of groups have a tree where the group X, that tree is nice. The fixed points are contractible, but the centralizer quotients, quotient with CGPs, are not contractible anymore. So you don't get an acyclic space from this tree that this group X. That is something, a problem in this line of thinking. You get a tree, that group X, infinite group X. It's a very nice tree, and its stabilizers are fixed points, are contractible with P subgroups. But when you mod out with the centralizer CGP, you have homology. So that's why they can't be used directly themselves.
Mm. Okay, thank you.
Okay, maybe it's a good point to thank Ergun for this great talk. And if there are further questions, we can have them afterwards. Okay, thank you very much.
Thank you.